Hello students, welcome back. In this video, we are going to do just one thing, rather technical proof of, wrong cell. Rather technical proof of this dimension lemma. Let capital V be a vector space and let V1, V2, V3 all the way to Vm generate the vector space V. And W1, W2, W3 all the way to Wn are linearly independent. Then m is greater than or equal to n. Okay. Generators tend to be more. Linear independent tend to be less. Okay, let's begin. We're going to use proof by contradiction. Suppose that the conclusion is false and we begin by m is strictly less than n. Alright? And then in the end, we are going to get a conclusion. We are going to get a contradiction. Okay, alright. V1, V2, V3 all the way to Vm generate capital V. So every vector in capital V can be written as a linear combination of V1, V2, V3 all the way to Vm, right? That is the definition of generating. In particular, we're going to apply this to W1, W2, W3 all the way to Wn, because these are vectors of V2. Conclusion, here we go. For W1, we have to have a linear combination, and we're going to run out of alphabet pretty soon, so we have to use these double indices. So indices may be a little bit difficult to follow. You don't have to pay all those special attention to the location of all those indices, not just yet. When you have matrices, then yes, true, we have to do that, but at this point, no, not really. Just remember this is a linear combination. Coefficient times V1, coefficient times V2, blah, 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 coefficient times Vm, alright? Let's go to the second equation. Same deal. Coefficient times V1, coefficient times V2, dot, 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 coefficient times Vm, repetition of all that. So each entry, W1, W2, W3 all the way to Wn, they're all linear combinations of V1, V2, V3 through Vm. Okay? Does everything make sense? Alright. And then we do some rather ingenious algebraic manipulation. This is the most technical and tricky part. Okay, here we go. In order to help you understand, I did a bit of a color coding, but we are not going to use those yet. So rewrite all this with a little bit of color coding, but the same thing. W1 is a linear combination, W2 is a linear combination, and all the way to Wn, that 2 is a linear combination of V1, V2, V3, all the way up to Vm. And then we just multiply a certain real number x1 to both left-hand side and right-hand side, x2 to both left-hand side and right-hand side, dot, 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 xn to both left-hand side and right-hand side. Is that true? Oh, yes. If you have an equality, you can multiply the same number to both left-hand side and right-hand side. No problem there. And what are those real numbers? x1, x2, x3, all the way up to xn? We don't know those yet. We will determine those a little bit later, and we're going to determine those by setting up appropriate system of linear equation, but that's way later. At this moment, just understand this. Each equation manipulated by multiplying the same number to left-hand side and right-hand side. Okay? Alright. And then here I just add up all those left-hand side. x1, w1, x2, w2, x3, w3, all the way up to xn, wn, and add them all up and form a linear combination. Make sense? To the left-hand side? Okay, we did that to the left-hand side. We have to do the same thing to the right-hand side. The first equation is for w1, so we have this for w1. And then this is x2, w2, and then repeat, 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 xn, wn. So far, just tedious, nothing fancy. And now, Let's rearrange all this addition and a little bit of multiplication, because you see multiplications are distributive and additions are associative and commutative, so we can rearrange accordingly with respect to all those coefficients of V1 with all those blue together, and then V2 and all those red together, and so on and so forth, Vm with all those green together. From here to there is nothing more than some algebraic manipulation using the distributivity, commutativity, and associativity of addition and multiplication of real number arithmetic. Let's recap. W1, W2, all the way to Wm are generated by V1, V2, V3, all the way up to Vm. So we have those linear combinations. And then for each equation, multiply by x1, x2, and xn respectively. And then add them all up to get linear combination. That's the left-hand side and also the right-hand side. And then the right-hand side, as complicated as it looks, you can just rearrange them using appropriate color coding. Then you get these. Okay, all right. Why did you do this? That's going to be answered in the next step. We're going to set each parenthesis equal to 0. That is 0, or 0, 0, and then that 2 is equal to 0, like this. Blue equation, red equation, dot, 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 green equation. Basically, coefficient of V1 is 0. Coefficient of V2 is 0, blah, 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 blah. And coefficient of green is equal to 0. We ended up with a system of linear equations. By the way, in this system of linear equation, we don't have any vectors. You see, W's are vectors, V's are vectors, but we are just using each coefficient part, the scalar part, another scalar part, and then the last scalar part. So we have just system of linear equation of real numbers. Now, how many equations are there? There are total m equations. M equations. How many unknown variables? N variables. x1, x2, x3, all the way up to xn. Oh, we have more unknown variables than the number of equations. So this system is not well posed. There must be infinitely many solutions. We don't need infinitely many. All we need is just one non-trivial solution. By the way, we're talking about this to tell the truth. In module 4, this theorem, you see, if you have more unknowns than number of equations, then there's at least one, consequently infinitely many non-trivial solutions. And the proof was, oh boy, we used mathematical induction and some rearranging without loss of generality, all kind of things. It was really hard, but the conclusion was very to the point, and then it made sense. If you have more unknowns than the number of equations, then we have infinitely many solutions. We have non-trivial solutions. So, in particular, we have a non-trivial solution, x1 bar, x2 bar, x3 bar, all the way up to xn bar. Not all of them is equal to 0, because this is non-trivial solution, and they satisfy this system of linear equations. So you can write like this. x1 bar satisfy the first equation. x1 bar, x2 bar, x3 bar, all those satisfy the first, second, third, all the way up to last equations. This system and that system exactly the same, and it applies for a particular non-trivial solution, x1 bar, x2 bar, all the way up to xn bar. Not all of them is equal to 0, okay? How does that help? Let's go back to here. x1 w1, x2 w2, plus all the way up to xn wn equal to that. and each coefficient became the equation of the system, right? And now we have solutions, so we're going to put those solutions back into these. In particular, I'm talking about this. Can we see this in same viewing window? Okay, x1, w1, x2, w2, all the way up to xn, wn. Now we have x1 bar w1, x2 bar w2, all the way up to xn bar wn. These are actually solutions, non-trivial solution. The solutions, therefore, each equation is 0. That equation is 0. And then that equation, that 2 is 0, you see? They're all zeros. You see, they're all zeros. So conclusion, 0 v1, 0 v2, dot dot dot, 0 vn. Add them all up, what do you get? We had to have the 0 vector. What's the conclusion do we have? This linear combination led to the 0 vector, yet not all coefficient was 0. This was non-trivial solution. So this linear combination is 0, yet not all these, not all of x1 bar, x2 bar, all the way up to xn bar is 0. Non-trivial. So this contradicted our assumption that w1, w2, wn, that's linearly independent. Because you see, what do you mean by linearly independent? What do you mean by linear independent? Whenever you have linear combination that led up to 0, 0 vector, all coefficient must be 0. Right? Wait a minute. There's a typo. Excuse me. Linear independent means all coefficient must be 0. Linear dependence must be not all of them has to be 0. Linear independent, all those has to be 0. Now, what did you get? Non-trivial solution. Where are we? Non-trivial solution. So not all of them are 0. Yet we ended up with a 0 vector. So w1, w2, w3, all the way to wn are linearly dependent. However, that contradicts our assumption that they were linearly independent. There goes a contradiction. We started from taking m strictly less than n. That was the conclusion, right? So we started from negating the conclusion, and then we ended up with a contradiction. That completed the proof. And just a short reminder, how did he use this proof? How did he use this dimension lemma? Excuse me, we use it over here. We have two bases, v's and w's, and this generate these linearly independent first. So these generate these linearly independent, so m is greater than or equal to n, exactly over there. And then we took the other point of view. These generate and those linearly dependent. Those generate and those linearly independent. Therefore, now n is greater than or equal to m by the same idea. In conclusion, m and n are the same. And this was integral in establishing the concept of dimension, because what if I select two different bases? Am I going to get the same number of basis vectors so that we have a well-defined concept of unique dimension? We just proved it, including the dimension lemma, the technical detail.